Question 2, Part B. In the diagram, OABC is a trapezium with OA parallel to CB. The coordinates of O, A and B are 0, 0, -1, 1 and 4, 6 respectively. Part 1. Calculate the length of OA. We can use Pythagoras' theorem to find the length of interval OA if we consider OA to be the hypotenuse of a right-angled triangle drawn around it. Now, the lengths of the two short sides are identical at 1 unit each, so using Pythagoras' theorem, OA squared is equal to 1 squared plus 1 squared, which equals 2, but we want the length of OA, not OA squared, so we'll need to take the square root of 2 to find the length of OA. So the length of OA is square root of 2 units. Part 2. Write down the gradient of the line OA. The gradient or slope of interval OA is equal to the change in y divided by the change in x, going from left to right. So starting at point A, the y coordinate is 1, and we're going down to point O, which has a y coordinate of 0. So the change in y is -1. Now the change in x, if we're starting at -1, and going to 0, the change in x is +1. Another way to look at it is rise over run, or rise divided by run. The rise is -1 and the run is +1. So the gradient OA is equal to -1 divided by 1, which equals 1. Part 3. What is the size of angle AOC? Let theta equal the angle of inclination of line OA to the positive x-axis. Here's the positive x-axis, here's line OA, here's angle theta measured anti-clockwise from the positive x-axis. Now in part 2 we found the gradient of line OA, which is -1. So we can use the formula tan theta equals m, where m is the gradient of the line, to find the size of angle theta. Now tan theta is equal to -1, since m is equal to -1. Rearranging this equation to make theta the subject, and we do that by taking the inverse tan of -1. So theta is equal to inverse tan of -1, which equals to 135 degrees. Therefore angle AOC is equal to 135 degrees. Another way to find angle AOC, or angle theta, is to consider the right-angled triangle around interval OA, finding the angle relative to the negative x-axis and then noting that the angle that we just found and theta are supplementary since they're angles on a line. Now the right-angled triangle around interval OA is an isosceles triangle where the two short sides are 1 unit each, which means that the two angles, other than the right angle, are 45 degrees each. So if that's 45 degrees there, angle theta is supplementary to 45 degrees, which means theta is 135 degrees, or angle AOC is 135 degrees. Part 4. Find the equation of the line BC and hence find the coordinates of C. Line BC is parallel to line OA, which means the gradients of both lines are identical. So gradient BC is equal to gradient OA, which equals -1, and we found gradient OA in part 2. Now the point B, 4, 6, lies on BC. So we have a gradient, we have a point. So using the point gradient formula, we can find the equation of BC. Now the point gradient formula, if you recall, is y minus y1 is equal to m times x minus x1 in brackets, where m is -1, y1 is the y coordinate of point B, which is 6, and x1 is the x coordinate of point B, which is 4. So y minus 6 is equal to -1 times x minus 4 in brackets. Expanding the brackets on the right hand side, we get y minus 6 is equal to -x plus 4. Taking the -6 on the left hand side, moving it over to the right hand side, it becomes +6 or +6, collecting the like terms, so +4 plus 6 is plus or +10, so y is equal to -x plus 10. Let's call this equation number 1. Now the y coordinate of C is 0 since it lies on the x-axis. Hence, from equation number 1, if we substitute 0 for y here, and then solve for x, we get 0 is equal to negative x plus 10, so x is equal to 10, which corresponds to the x coordinate of point C. Therefore, the coordinates of C are 10, 0. Part 5. Show that the perpendicular distance from O to the line BC is 5 root 2. On the diagram, I've sketched the line that represents the perpendicular distance from the point O to the line BC, and it meets the line BC at the point D. Now this angle here is a 90-degree angle because it's a perpendicular distance, so we've formed a right-angled triangle ODC. The next thing to note is that this angle here and this angle here are corresponding angles because they stand on parallel lines. AO is parallel to BC. The x-axis is the transversal in this case. In an earlier part, we found the size of this angle here to be 45 degrees, which means angle DCO must also be 45 degrees. That means angle DOC must also be 45 degrees because the angle sum of a triangle is 180 degrees. So we formed a right-angled isosceles triangle where this side, so this is the side marked with a lowercase d, is equal to this side here, also marked with a lowercase d, and OC represents the hypotenuse of this right-angled isosceles triangle. So we can use Pythagoras' theorem to find the length of the perpendicular distance. So I've written some reasoning here. Angle DOC equals angle DCO, which equals 45 degrees, hence triangle ODC is isosceles, hence OD equals CD, which equals lowercase d. Now angle ODC is equal to 90 degrees, hence triangle ODC is also right-angled. Now OC is equal to 10 units, which is the length of the hypotenuse of triangle ODC. So by Pythagoras' theorem, d squared plus d squared is equal to 10 squared. 2d squared is equal to 100. Dividing both sides by 2 to make d squared the subject, we get d squared is equal to 50. Taking the square root of both sides, we get d is equal to the square root of 50, which simplifies to 5 root 2. Therefore, the perpendicular distance from O to BC is 5 root 2 units as required. Part 6. Hence or otherwise, calculate the area of the trapezium OABC. To find the area of a trapezium, we need the lengths of the two parallel sides and the perpendicular distance between them. Now the length of OA we found in part 1, which is root 2 units, and the perpendicular distance between OA and BC, which we found in part 5, is 5 root 2 units. We need the length of BC, however. Now we can use the 2-point distance formula to find the length of BC because we have the coordinates of point B and point C. So using the 2-point distance formula to find the length of BC, we have BC squared is equal to 10 minus 4 in brackets squared plus 0 minus 6 in brackets squared, which evaluates to 72. So BC squared is equal to 72. Taking the square root of 72 to find the length of BC, we get BC is equal to root 72 or 6 root 2 units in simple surd form. Now the area of trapezium OABC, we can find using the area of a trapezium formula. That's half times the perpendicular distance times the sum of the parallel sides. So in this case, it's half times OD times OA plus BC in brackets, which equals half times 5 root 2 times root 2 plus 6 root 2 in brackets, and that equals half times 5 root 2 times 7 root 2, which simplifies to 35. Therefore, the area of OABC is 35 square units.